bright future. Every student matters.
Hello dear students, till now we have studied about the Fleming's left-hand rule and the principle of electric motor. In that Fleming left-hand rule, what we saw was that if a current carrying conductor is placed in a magnetic field, then it experiences a force, right? So if I try to relate what we have studied till now is that the current carrying conductor was placed in a magnetic field. So there was a wire which carried current, right? That means I was there and it was placed in a magnetic field. Fine, magnetic field, we represent this magnetic field, let us say with F, right? So there was a magnetic field. The current carrying conductor was present in there, let it be MF, not to get confused. Then we saw that a force acted on that wire and produces motion, right? Let us be representing it with capital M, motion. Fine. Now if we take the opposite of it, that is, if we take a magnetic field and we produce motion in a wire by applying some force, then we observe that current is induced in that coil, right? Now this is very important to understand the two basic differences between this thing. First thing was when we have studied about Fleming's left hand rule. In that Fleming's left hand rule, I repeat, please try to relate, don't get confused. In that Fleming left hand rule, we studied that current and magnetic field, these two things were present and motion was produced in the wire. Now what we are talking is, we are talking that the magnetic field and motion, two things are present, and now we will see that current is induced in the wire. So if we have got these three things out of current and magnetic field and motion, till now we have studied that these two were given to us and we observed that motion was produced in the wire. But now what we are saying is, out of current, magnetic field and motion, magnetic field and motion if provided, then current will be induced in the coil. Understood? Let us do an activity to observe the same thing. In this activity, what we will do is, we will take a magnetic field. We have taken this magnet, North Pole and South Pole. What we'll do is, we'll take a wire. This is a metallic wire which is a good conductor of electricity, right? And we just connect it with a galvanometer. Now we know what exactly a galvanometer is. A galvanometer is a device which detects the presence of current. Fine. It will tell us whether the current is present or not. Initially, this galvanometer pointer is at this middle 0 reading. Whenever there is current, it will deflect either to the right or to the left. Fine. So when we connected this metal wire with the galvanometer's pointer pointed towards the center, that is the 0 reading. Now what I did was, I will force this wire in the upward direction. Now when I force this wire in the upward direction, I found there was a deflection in the galvanometer, and the deflection in the galvanometer signifies that there is some current in the wire. Now how did that current come? That current basically came because of the same concept that we studied right now, that if in a magnetic field some force is applied and motion is generated in a wire, then current gets induced. This is probably because the magnetic lines of forces which were going from north to south, when this wire cuts those magnetic lines of forces, some ionic charges produced in the wire. Right. Now, when I did the opposite of it, now what will I do is I will move the wire in the downward direction. Now, when I moved the wire in the downward direction, again I saw the galvanometer pointer deflected, but now it deflected in the opposite direction. Now, this is a very important observation which shows that by changing the direction of motion or the direction of force on the wire, the direction of current is induced, no doubt, but the direction of current, it also gets opposite, gets changed, right? So these two things, they were related, and in order to find the direction in which the current is induced, Fleming himself, who has given the left hand rule, Fleming gave the right hand rule. Now, what did he say in this Fleming right hand rule? He said the same as he had done in the left hand rule, right? What he said in the left hand rule was, just look at my hand, look at my fingers, right? In the left hand rule, we had this concept that we have studied in the previous class, that place your forefinger, middle finger and thumb in such a way that they are perpendicular to each other, right? Similarly, the same thing we have to do with the right hand. In the right hand also, I will take the thumb, right? I will take the forefinger and I will take the middle finger in such a way that they are perpendicular to each other. Everything is same, right? The forefinger in both the cases, whether it was left hand rule or the right hand rule, the forefinger, like this, represented the direction of magnetic field lines, which is from north to south, right? The thumb is the direction of motion or the force. In the left hand rule, the middle finger is the direction of current, whereas in right hand rule, there is a slight difference. The difference is that now the middle finger will be the direction of induced current, means that current that has been induced or generated in the wire. Fine. In left hand rule, these two things, the forefinger and the middle finger, the magnetic field and the current, these two were given, and we were using the left hand rule to find the direction of thumb, that is motion. In right hand rule, now we'll be provided with the direction of magnetic field as well as the direction of motion, and now we will be using this right hand rule in order to find the direction of middle finger, that is the direction of induced current. Got it? Now let us see. So this is basically the Fleming's right hand rule, in which this middle finger is the direction of induced current, this forefinger is the direction of magnetic field, and this is thumb in the direction of motion. This is of our right hand, right? Fine. So this is basically what Fleming's right hand rule states. Now, as per the left hand rule and right hand rule, in both the things we observed that in, let us relate the left hand rule and the right hand rule. The left hand rule, we said that the direction of current and direction of magnetic field were perpendicular to each other, because of which force was generated, and this force was perpendicular to both the current and the magnetic field. Similarly, in right hand rule also, the first difference is that the magnetic field and now the force are given to us, which should be perpendicular, and then the current will be induced in the wire, and this induced current will once again be perpendicular to both the magnetic field as well as force. This is quite important, that if we move a wire perpendicular in a magnetic field, only then current is induced. But if we move the wire parallel to the direction of magnetic field, then no current will be induced in the wire. Got it? Right? So this is our concept of induced current. And when this type of current is induced by rotating or moving a wire, this is known as EMI, or it is known as electromagnetic induction. This is electromagnetic induction. We will see it in a bit detail when we will be inducing current, right? So this is the basic concept of electromagnetic induction. Fine. Now, if I want to increase the amount of induced current, then I will see a few things. What? Let us see. First of all, let us try to relate. Number one, there are the magnets and there is a wire, right? If I keep the magnets, just try to once again relate my hand. Like, for example, this is, let us see, relating to, just try to observe with my hands. This is the magnet, north pole or the south pole, right? This is a wire that I have taken, right? If I will move the wire perpendicularly, right? These are the magnetic lines of forces going from north pole to south pole. Got it? If I move the wire perpendicularly in between this magnetic field, then only current will be induced. Now, very, very important. First thing is, I'll keep the magnet stationary and I will move the wire. Current will be induced in the wire. This is the first thing that we observed, right? The second case may also be possible, that I keep the wire stationary and I keep the magnet moving. Then also I will see that current will be induced in this wire, because the purpose is to cut the magnetic field lines through this wire. Alright. Now, if I move both the things simultaneously in such a way that these magnetic field lines are not getting cut with the wire, no current is going to be induced in the coil. Got it? So this is quite important to understand. What? That there should be one thing moving with the other thing stationary, whether it is the magnet moving or the coil moving. If there is a relative continuous motion simultaneously of both the things, no current is induced. First case. Second thing, if I move the wire parallel in between this magnetic field, then also it is observed that no current is induced. Right? Fine. Now, if I increase the strength of the magnetic field, more amount of current will be induced. If I'll speed up the motion by applying more force on the wire, more current will be induced. And very importantly, I saw that when the wire was brought down, the current was induced in a particular direction. When the wire is brought up, the current changes its direction. How it happened? Just try to relate once again the Fleming's right hand rule. In this, I said that this is the magnetic field, my forefinger. Initially, I was applying the force and bringing the wire in the upward direction represented by my thumb. The direction of the current was this, towards my left, right? But when keeping the forefinger same in your direction and by changing the direction of motion, now the forefinger is still in your direction. That means the magnetic field lines are still in your direction, but now I am bringing the wire down. So you see, now the direction of my middle finger, that is the current, has just been towards my right. I relate it again. This is when the wire is brought down. The direction of current you can see is in this direction. If I move the wire in the upward direction, because thumb is representing motion or force, then the current changes its direction. And this is what we see in this particular next activity. Please try to relate. Alright. Let us see. What we do is, we take a wire, right? This is a wire AB, which is connected to a galvanometer, right? Initially, the pointer must have been at this particular 0 reading. Got it? We took a magnet. Now what we did was, we just inserted and pushed this magnet inside this coil. What will we observe? We will observe that the galvanometer deflected towards one side. The right hand side is this, in this particular instance, it is moving in the right hand side. Alright. So if I push a magnet inside a stationary coil, then two things happened. One, the current is induced in this coil, because of which there is a deflection in the galvanometer. Got it? Now what I do is, I pull this magnet out of this coil. If I pull this magnet out of the coil, once again current will be induced in this coil, but now importantly, because the direction of motion of the magnet is opposite, initially it was inside the coil, right? Now it is pulling it away from the coil. So therefore current is induced, no doubt, but the galvanometer is pointing in the opposite direction. So this is very, very, very important. This is a 3-marker question which normally you encounter. Let's try to relate. There are 3 things. One thing asked to you will be, what happens if a magnet is pushed inside the coil? Right. So the magnet is pushed inside. Next part, the magnet is pulled outside the coil. And the third part is that this magnet is held stationary in the coil. These are the 3 options you will be asked. So the answer that you will be giving us is trying to relate. Please try to relate it. If a bar magnet is pushed inside the coil, current will be induced in it, and the galvanometer will deflect. It will point towards one side. Which side we don't have to mention. When it is pulled outside, once again the current will be induced, but now the galvanometer will point towards the opposite side, right? So we have to just specify to one side, to the other side, to one side, to the opposite side, left or right, we don't have to specify. And third case is quite important. When this magnet is pushed in, and if it is held stationary inside the coil, then no current will be induced, and hence there will be no deflection in the galvanometer, and the galvanometer will point towards the center, that is the 0 reading. So this is a very important question that you encounter. Many a times you have just seen this question, many a times it is asked, right? So this is about a few concepts related to this right hand rule.